In this video, we are going to treat homogeneous reactions for non-elementary behavior. We will have a non-elementary formation of hydrogen iodide from the constituents of hydrogen molecule and iodine molecule, a multi-step complex reaction scheme. We are going to derive the rate expression, and we will learn quasi-steady state, pseudo-steady state, and quasi-equilibrium conditions of the chemical kinetics. Now let's begin with writing the reaction. The overall reaction is formation of two hydrogen iodides from the constituent molecules, dihydrogen and diiodide. We will start with the formation of iodide radical from the molecule, dissociation of iodide into its radicals, and then this radical, iodide radical, will react with hydrogen molecule to form one hydrogen iodide and one hydrogen atom, another radical, and a hydrogen atom, let's say. Let's not call that as a radical, but it's a short-lived intermediate, and this hydrogen atom reacts with an iodide atom to form another hydrogen iodide. The net reaction goes as follows. Here we have two iodide molecules formed. This cancels with this one and this one. We have two hydrogen atoms formed. We have one hydrogen atom formed. This cancels with this one. And we have, when we sum up these, we obtain I2 plus H2, forming 2HI. This is the net reaction. Now let's move forward and write what their rates might be. I will call this reaction 1, 2, and 3. And the rate of this reaction will be rate forward 1 minus rate reverse 1. Similarly, the rate of the second reaction will be rate forward 2 and rate reverse 2. And the third reaction will be rate forward 3 minus rate reverse 3. So this is the first rule that we have, that all the reactions have their reverse components. Whether those reverse components are as large as the forward components determines whether the reaction is at equilibrium or not. This is the first rule. And the second rule is about the elementary kinetics. For the elementary kinetics, let me call this rule 1. And a rule of the elementary kinetics. The rule of elementary kinetics is such that the rate of an elementary step is equal to its rate constant k let me call this forward or reverse times the concentration of the species that are involved in that step raised to the power of their stoichiometric coefficients, and they are multiplied. All right? Multiplication of all the concentrations raised to the power of their stoichiometric coefficients. Now when we apply these rules into individual steps, we will get a general matrix of rates, general matrix of processes. Now let's also generate our reaction rate versus chemical species matrix, which will help us in analyzing this whole reaction network. So I'm just following this line, and let us not call this R, but let us call this step 1. Step 1, step 2, and step 3. So we have components as I2, I, H2, as they appear in the reaction network, H2, H, and HI. So we're going to form our stoichiometric coefficient matrix. I2 in reaction 1 has a stoichiometric coefficient of -1. I has 2. These have 0 stoichiometric coefficients. In the second step, I2 has 0, I has -1, H2 has -1, H is +1, and HI is +1. In reaction 3, I2 is again 0, I is -1, H2 is 0, H is -1, and HI is 1. So, with that, let us begin writing the forward and reverse rates. I will continue here. Rate 1 is equal to, I will apply this rule, or perhaps using this domain is better. We're going to have rate 1 is equal to rate forward 1, K forward 1 times concentration of iodide molecule raised to the power its stoichiometric coefficient, which is 1, minus K reverse 1 times concentration of the atomic iodide, iodine atom raised to the power 2. Rate 2, K forward 2 times concentration of iodine atom raised to the power 1 times concentration of hydrogen raised to the power 1 minus K reverse 2 concentration of H and concentration of HI. Let's divide our board. And rate 3 is K forward 3 concentration of I times concentration of H minus K reverse 3 times concentration of HI. So we have our rates at our disposal. We have our stoichiometric matrix. This is the mechanism that we have to deal with, and our objective is to come up with a rate expression with functionalities, with dependencies on temperature and on concentrations of measurable species such as iodine, hydrogen, and hydrogen iodide. here we assume that hydrogen atom and iodine atom are short-lived intermediates. Well, given the complexity of this system, despite that we have to deal with only 2 long-lived reactants and 1 product and 2 short-lived intermediates, we would like to come up with an overall rate expression. Let us see where the algebra is going to take us. Now, this domain I will use to write the time rate of change of the concentrations of the individual components, thinking that we are dealing with these reactions in a batch reactor. Remember, the batch reactors are not necessarily the batch reactors themselves. Sometimes a small fluid element can be treated as a batch reactor, as we have been doing in a plug flow reactor. We were selecting a small fluid element which doesn't interact with the fluid package in front of it, neither the behind. So it is treated as a batch reactor. Or we had ping pong balls in a segregated flow reactor model. So we're going to monitor the rate of change of concentration of these species in a constant volume batch reactor. Let us start from I2. dI2 over dt is equal to R1, rate of the first reaction. di over dt is equal to nu I2 times R1, and hence this is equal to minus R1. This is nu I of nu I2 in reaction 1. So this is nu I in reaction 1 times R1 plus nu I in reaction 2 times R2 plus nu I in reaction 3 times R3. Nu I in reaction 1 is equal to 2. Nu I in reaction 2 is equal to minus 1. And nu I in reaction 3 is equal to also minus 1. So let's clean this up to write di over dt to be equal to 2R1 minus R2 minus R3. Now, I'm not going to repeat that for the others. I will just write their final form. dH2 over dt is equal to minus R2, and that's it. dH over dt is equal to R2, it's produced by R2, R2 minus R3. And then finally, we have dHi over dt, which is equal to R2 plus R3. And those R1s, R2s, R3s are expressed in terms of their individual rate constants and the concentrations. So we have a set of ordinary differential equations, and differential equations are not in the most situations suitable to have a rapid analysis of the reaction. So we will try to make approximations and assumptions and derive the final rate expression, hopefully in an algebraic form. So let's see. Now, here we have short-lived intermediates. We would like to eliminate those short-lived intermediates from the end rate expression. So now we have time derivatives, and the time derivatives in our rate processes may have meanings as they approach to steady state and as they approach to equilibrium. Now let us define what do we understand from steady state and what we understand from the concept of equilibrium. Now, concept of d over dt of any term, right? Or maybe it is better that I write this over here to guide us for the rest of the lecture. D over dt of any parameter being equal to 0 may refer to several things. That parameter is constant, okay? And for our processes, it means that we are at steady state. Okay, for processes. Or they may mean that we are at equilibrium if we are observing the states of the system. So steady state is a process attribute. Equilibrium is a state attribute. So when we have time invariance, in other words, parameters are not changing with respect to time, it might mean that we are at steady state. It might mean that we are at equilibrium. Whether it is at steady state or at equilibrium depends on whether we are looking at a process or we are looking at a state. Now, let's look at our process. This whole reaction network is a process. So, for the process, things should be time invariant. For the overall process, things should be time invariant. In other words, for the whole process, the I2 over dt should be 0 when the process reaches equilibrium. The H2 over dt should be at equilibrium. All right, so let's invoke those process attributes into the individual steps, and let's see where it is going to take us. So I'm going to continue here. di2 over dt is equal to 0. By writing that, I invoke quasi-equilibrium hypothesis that this first reaction is equilibrated. So it says that rate 1 is equal to 0, or rate forward 1 minus rate forward 2 is equal to 0. Rate forward 1 minus rate reverse 1 is equal to 0. Or rate forward 1 is equal to rate reverse 1. Okay, this is rate forward 1, this is rate reverse 1. They should be equal to each other. I continue. K forward 1 times Ci2 is equal to K reverse 1 Ci square. Now remember, I was trying to eliminate the short-lived intermediate concentration, which this, after making the quasi-equilibrium assumption, this relationship allows me to do. So I get Ci to be equal to square root of K forward divided by K reverse is equal to K equilibrium 1 overall times Ci2 in square root. Now I expressed the concentration of the short-lived intermediate in terms of the concentration, measurable concentration of my reactant. Now let me see if I can do something similar for the steady state concentration of hydrogen. dH2 over dt is equal to 0. dH2 over dt is equal to minus R2, or it is R forward 2 minus R reverse 2. Just being that only one step is involved, also allow me to label that as a quasi-equilibrium condition also. By the same logic, I continue. Rate forward 2 is equal to rate reverse 2, or K forward 2 times Ci times CH2 is equal to K reverse 2 times CH times CHI. And this expression allows me to obtain the concentration of the short-lived intermediate of hydrogen atom. I get CH as K2 times Ci times CH2 divided by CHI. And I know already CI is going to be provided here. Now I have concentration of short-lived intermediate H in terms of the concentrations of iodine molecule and hydrogen molecule. Now, for this simple reaction network, it turned out that the first step is under quasi-equilibrium condition. The second step is under quasi-equilibrium condition. All right. And let's take this third step as the rate determining step. Right now, everything is arbitrary. After we finish the derivations, we will discuss the implications of those assumptions and how we are going to remove those assumptions. Now, if the rate of the third step is the rate determining step, the overall reaction rate should be equal to K forward 3 times concentration of H times concentration of I minus K reverse times concentration of HI. Now I'm going to substitute concentration of H and concentration of I from here, and I will analyze this rate for the initial periods of the reaction and for the conditions that time goes to infinity. This rate is equal to K forward 3 times concentration of H times CH2 divided by CHI times concentration of I here, concentration of I here one more time, so concentration of I raised to the power 2, that is equal to K equilibrium 1 times CI2. Minus K reverse 3 times CHI. I will do a little bit of cleaning of the algebra. We have K forward 3 times K equilibrium 1 times K equilibrium 2 times CH2 times CI2 divided by CHI minus K reverse 3 times CHI. So we have derived a rate for this reaction network where we have taken some of the steps as equilibrated, and we have taken step number 3 as the rate determining step or kinetically relevant step. And we have a rate expression in terms of measurable quantities of reactant concentrations and the concentration of the product molecule. Now, after we finish this derivations, we are going to now analyze the limiting conditions. Limiting conditions are the periods where time goes to 0 and time goes to infinity. Now let's begin with time goes to 0 conditions. So let me use this domain for the conditions as time goes to 0 in the beginning of the reaction. Now, in the beginning of the reaction, we do have only the reactants, no products. So, in the beginning of the reaction, we cannot talk about reverses of the steps. We can only have forward reactions. Okay? So let's take the first one, which we have taken as an equilibrated step. But we cannot take that as an equilibrated step in the early periods of the reaction. In the early periods of the reaction, there is no iodine atom. There is no iodine atom. This concentration is 0. There is no reverse. We have only the forward step. In the early steps of the reaction, we have no iodine atom. This step has not been triggered yet. So is this one. So there is a trickle effect that first we have to form the products, which will enter into the reaction to go back to the reverse. So at time approaching to 0, rate 1 is actually only K forward 1 times Ci2 when time is equal to 0. When time goes to infinity, on the other hand, this is the second limit that we have to discuss. As time goes to infinity, the reaction goes to completion. All of the steps reach equilibrium. The first one is at equilibrium, the second one is at equilibrium, and the third one is also at equilibrium. All right? So we have already treated the first and second steps to be at equilibrium. Let's see if R1, R2, and R3 are equal to 0. They are equilibrated. Now with that, let's look at this rate expression where we have rate to be equal to, overall rate to be equal to R3. Let us obtain the equilibrium relationship from this. We said that at equilibrium, R3 is equal to 0. R3 is equal to 0 also. And this expression is equal to 0, which gives us the following relationship. K equilibrium 1 times K equilibrium 2 times K equilibrium 3 to be equal to CHI squared divided by CH2 times Ci2. And this is equilibrium constant of the overall reaction. Now, this is an important conclusion that we have arrived here. In this derivation, we have established what we understand from quasi-equilibrium, from rate determining step, and also we have derived the equilibrium constant of the overall reaction as the multiplication of the equilibrium constants of the individual reactions. This expression is going to give us the opportunity to do thermodynamic consistency tests. So let us treat the equilibrium condition of these reactions and relate the equilibrium constants to the equilibrium constant of the overall reaction, as we have related so far. But let us begin with the fact that each of these reactions have an enthalpy change associated with it. Right. Delta H1, delta H2, delta H3, and of course, delta H overall. Delta H of each of these reactions are the differences of the forward and reverse activation energies. And here we have an expression telling us that the overall equilibrium constant is equal to the multiplication of the individual equilibrium constants. So let us work through this example, the relationship between the enthalpy changes and the equilibrium constants by starting from the fact that equilibrium constant is equal to e to the minus delta g over RT. So I'm going to carry this expression, K overall equals K equilibrium 1, K equilibrium 2, K equilibrium 3. And then I will substitute the free energy change relationship in that. So K equilibrium overall is equal to K equilibrium 1, K equilibrium 2, and K equilibrium 3. They are all going to be raised to the exponentials. If I take the logarithm, natural logarithm of both the right side and the left side of the equation, I should be getting a summation. So let's do that. Minus delta G overall, then should be equal to minus delta G of 1, minus delta G of 2, minus delta G of 3. Delta G is equal to delta H minus T delta S. So let's substitute that. Minus delta H overall plus T delta S overall is equal to summation starting from 1 to 3 of delta H I minus T delta S I. Let's do that for the space sake. Now, we are going to combine similar terms together. Similar terms are, we have a temperature-dependent term group, and the temperature independent term group. So on the right side and on the left side of the equation, they should be identical. So we have delta H overall is equal to delta H1 plus delta H2 plus delta H3, and delta S overall is equal to delta S1, delta S2, and delta S3. Now this establishes a guideline for us, given that delta H of the individual steps are forward and the difference between the forward and reverse activation energies, then by getting help from the overall reaction enthalpy difference, which is available to us through the thermodynamics charts, we can have a leverage to estimate some of the intermediate rate constants and their activation barriers through this set of relationships. The true estimation of the individual rate constants require that we go back to the first principles, and the rate constants, K0s, are best represented by the transition state theories. K0s can be obtained from transition state theory. And activation energies are best available through density functional theory. We have derived the basic expression of the transition state theory. We haven't derived the relationship between the molecular velocities and the velocity distributions. We will do so later. Density functional theory is a whole field in itself, but it gives us good leverage on the activation energies of the individual steps, because now in the first principle methods we are able to examine how those short-lived intermediates are related to the other intermediates in a reaction. Now let us discuss the concept of pseudo-steady state. Pseudo-steady state hypothesis. Remember the steady state. The true steady state is where the time invariance is established. However, we might be close to steady state, but not truly there. It's called the pseudo-steady state. Pseudo-steady state hypothesis. It's a hypothesis. It's subject to proof. But let us discuss the pseudo-steady state hypothesis through the reaction example that we are working on today. Now we have a reaction intermediate, short-lived intermediate, iodine. Now we have taken, under the conditions of the example that we were working on, we have taken the first step under quasi-equilibrated steps. Now I'm going to remove those assumptions. Let us see if we can remove those assumptions. Yes, the assumptions are now removed. Now we are going to invoke the pseudo-steady state hypothesis. So for the pseudo-steady state hypothesis, you're going to have d I over dt to be equal to 0. What was that? di over dt was equal to 2r1 minus r2 minus r3. that, and that, and that. Now let us say that we are at the early stages of this reaction. At the early stages of the reaction, at short enough periods, there is not sufficient I for the reverse reaction to be meaningful, but sufficient amount of I for the forward reaction of the second one to be meaningful. So our R1 is R1 forward only, and our R2s and R3s are also. Okay, they're only their forward components. Not enough products to have a meaningful rate in the reverse direction. R1 forward is K forward 1 Ci2 2 times di2 di over dt. It's 2 times R1 forward K forward 1 times Ci2 minus R2, and that is forward only, K forward 2 times Ci times CH2 minus R3. Times Ci times CH. You see now, under those conditions, we are going to obtain a very different expression for Ci than what we have derived under quasi-equilibrium conditions. Let's derive. From here, this should be equal to 0. This is a pseudo-steady state hypothesis. So we are going to derive Ci to be equal to 2 times K forward 1 times Ci2 divided by K forward 2 times CH2 plus K forward 3 times CH. We are going to invoke another pseudo-steady state hypothesis to substitute for CH. That is going to be the exercise for you. The objective of this segment was to demonstrate that at different stages of the reaction, relative rates may be different. Also, at different levels of conversion, that also means different stages of the reaction, their relative rates, rate forward 1, rate forward 2, rate reverse 1, rate reverse 2, they could be different. All right, and there is one more condition. Different stages meant that we have different concentrations of the reaction intermediates. There is one more condition, and that is that at different temperatures, the rate constants, K's, are going to be different, and hence, as a result, forward and reverse rates are going to be different. And how fast each of these reactions become depends on not only their concentration of the species involved in that reaction, but also the temperature. And as a result of the temperature, the rate constants will evolve differently, and therefore we might be facing different kinetically relevant steps and different steps that are under quasi-equilibrium. So we have to be very, very careful when invoking those assumptions. Those assumptions are strongly dependent on the state of the system in terms of concentrations of the individual constituents and in terms of the temperature. So when deriving all these equations, we have made some assumptions. One was quasi-equilibrium, one was pseudo-steady state hypothesis. There is a similar assumption for the surface reactions. It is called the most abundant reaction intermediate. Okay? So this quasi-equilibrium is about the reaction steps. Assumptions about reaction steps, quasi-equilibrium assumption about reaction steps, while pseudo-steady state hypothesis is about the intermediates. And most abundant reaction intermediate is also about intermediates. And how do we know assumptions about these? How do we decide? All right, assumptions about this are decided for the quasi-equilibrium. Those are decided from the external knowledge. External information is necessary, such as the one from spectroscopy. For a steady state hypothesis, pseudo-steady state hypothesis, we might invoke pseudo-steady state hypothesis by looking at the site balances, especially when we are invoking this for a surface reaction. But also, it has to be also supported from external information. For the most abundant reaction intermediate, has to be supported by the external information. External information, such as surface concentration of the most abundant reaction intermediate. Most abundant It's the short for the most abundant reaction intermediate. So, one more time, quasi-equilibrium is about reaction steps. this step is at equilibrium, for example, we need external justification eventually to firmly state that this step is at quasi-equilibrium. Pseudo-steady state hypothesis is about intermediates, and most abundant reaction intermediate is also about intermediates, and it is most abundant reactive intermediate is a frequently used assumption for the source reactions. Okay.